Hello everyone, and welcome to today's video. Today we're going to take a look at section 3.5, quadratic models using factored form. So our learning goal for today is to determine the equation of a quadratic model using the factored form of a quadratic relation. So first we're going to recall what we learned previously. So we're going to determine a quadratic equation in factored form when the zeros are at -1 and 5, and the function contains the point 1 and -4. So in general, when you are given these zeros in a question, you're going to start with the general form that contains the zeros. So in this case, that would be our factored form. So let's start with our general equation of what factored form looks like. So we get y is equal to a x minus s, x minus t, where the s and the t are our two zeros. So our next line, we can continue to substitute that information in. So we get x minus s is equal to -1, so we're going to put that in a set of brackets. X minus t is equal to 5, so we can just substitute that right into there. When you see these two negatives beside each other like that, in this multiplication here, we always have to simplify our equation. So these two negatives just like that, we are going to simplify to be x plus 1, and then we can copy everything else. So now what we're going to do is we're going to take our point 1 and -4, and we're going to sub it into our equation. So we're going to sub 1 and -4 into the equation to solve for the only missing variable, which in this case is a. So how that's going to look is we're going to, instead of y, so let's take our point here, we have x and y. Make sure to concentrate. We're going to have -4 is equal to a. Instead of x, we have 1 plus 1, and instead of x, we have 1 subtract 5. So -4 is going to be equal to a multiplied by 2 multiplied by -4. So this is going to be -4 is equal to a times -8. To get that a all on its own, we're going to take this side and divide by -8. What we do to one side, we must do to the other. When this and this cancel, we're going to be left with a is equal to, our two negatives here can cancel each other out. So we get 4/8. And we always have to make sure we have our fractions in the simplest form. So we can divide both the numerator and the denominator by the same number of 4. What we do to the top, we have to do to the bottom. So we can get our a value, which is equal to, fully simplified, 1/2. So therefore, we can write our final equation as y is equal to a. So we're going to look back at this one right here before we sub our point in. So we're going to get 1/2 for a, x plus 1, and x minus 5. So what we're going to focus on is using these skills, but instead we're going to get some information from our graph instead of the question explicitly giving it to us. So we can use quadratic models to represent things that occur in real life. So how to find the equation of a curve of good fit? So what we're going to do first is, given some data in a chart such as this below, we're going to plot the data, we're going to draw a curve of good fit and extend it so it passes through the x-axis. We're going to use the estimated or actual zeros and use them just like we did up here. Then we're going to find the value of a by subbing another point on the curve. It can usually be the vertex, but any single point will work. So let's look at this first example here. So data from the flight of a golf ball is given in the following table. If the maximum height of the golf ball is 30.0 meters, determine an equation for a curve of good fit. Okay, so we have our information here, a horizontal distance and the height. The horizontal distance is our x variable and the height is our y. When you are graphing, ensure that we have these two main things. Include the x and the y axes, and make sure we have the axes titles. So for x, we're going to write this as the horizontal distance, and for the y, we have our height. So we're going to go ahead and plot these points here. So the first one we have is 0 and 0, which is going to be right here. Then we have 30 and 22, so that's this point right here. We have 60 and 30. We have 80 and 27. And we have 90 and 22.5. So that's going to be potentially right there. So far we have these points here. A key piece of information that this question gave us is that if the maximum height of the golf ball is 30 meters, well, that means that this right here is the vertex, which occurs at 60 and 30. So since that's the vertex, we already know that the axes of symmetry can go directly through this, just like that. And we know it's going to be symmetrical on both sides. So we can see here our first 0, which is right here. And we can see from the axes of symmetry, it is 60 meters away. Remember, on the axis of symmetry, it is symmetrical on both sides. Since this 0 is 60 meters away, using the logic that we have, we know that the other 0 is also going to be 60 meters away. So we know that we're going to have this right here, and the golf ball is going to hit the ground at this 120 mark. So what we can do is now connect these points on the graph of our sketch. So again, we want to connect these. We're going to do a curvature at the end. It's going to come downwards like this, and we're going to connect to the 0 that we know over here. So we know, based off this diagram here, that these zeros in this case are going to be 0 and 0 and 120 and 0. So this means that S is equal to 0 and T is equal to that X value of 120. So what we're going to do now is determine the equation for the curve of good fit. So again, we're working with our zeros in this case. So we're going to start with our general equation in our factored form, which contains our zeros. So we have y is equal to a x minus s x minus t, where s and t are the zeros in our question. So we have y is equal to a x minus, the first one is 0. So we're going to do x minus 0, and then x minus the second 0 is at 120. So we can simplify this. Well, x minus 0 is simply just x. So we can simplify our equation to look just like that. So the only thing we're missing now is, again, this a value here. So what we're going to do is we're going to sub in a point in order to solve for that a. So in this case, again, we typically do substitute in the vertex. So we're going to sub in the point 60 and 30 to solve for a, where this represents the x and this represents our y. So looking at our equation, instead of y, we're going to substitute 30 into there. This is equal to a. Instead of x, we're going to substitute 60. And then we get 60 minus 120. And we just take it one step at a time and continue to simplify. So we're going to get 60, and minus 60. One step ahead of myself. When we multiply these two over here of 60 and negative 60, you are going to get 30 is equal to a negative 3600. To get this a all on its own, we're going to take this side and divide by negative 3600. What we do to one side, we do to the other. over on this side, this is going to cancel with this. So we're left with A is equal to 30, and we can say negative 30 over 3600. And we always want to put our fractions again in lowest terms. So these both have a common multiple of 30. So we're going to take our numerator divided by 30. What we do to the top, we do to the bottom. And this simplifies to A is equal to minus 1 over 120. So that means our final equation is we're going to again look to just right before we put our point in, which is right here. So that's going to be minus 1 over 120. Then we have x, which is all on its own. So we can simply just write that like this. And then our other bracket was x minus 120. And we can put that into a set of brackets. And there we have our quadratic equation that models our situation of our golf ball flying in the air and coming back down. So let's take a look at the second example here. So we have a parachutist that jumps from an altitude of 2,000 meters. So this table shows the distance of the parachutist from the ground after each 3-second period. So once again, make sure you have your axes labeled as x and y, and we put the titles. So in this case, our time is our x variable, and the height is the y variable. So graphing these points, it's going to look something like this. So we're going to start off with 0 and 2,000, which is going to be, let me just get rid of that quick. It's going to be right here. So we have 0 and 2,000. We have 3 and 1911. So approximately perhaps right there. 6 and 1650, so this is 17, so we're perhaps going to go something like this. 9 and 1215, so this is 1250, so let's go somewhere here. And we got 12 and 608, so this is 750, 600, perhaps maybe we'll say something like this. Okay, with these numbers, you're not going to be 100%. We want to try to get as accurate as we can. So what we're going to do is draw a shape that looks perhaps something like this. And this is going to continue that curve. And we're going to estimate that it goes and hits our axes at this point right here, which is that value of 13. So based off the question like this, which is the parachutist, okay, they're jumping from this altitude and they're immediately going down on this side. If we were to examine this going this way, okay, this point here is going to represent the tallest point that it can go, jumping out of that plane. So because it's the maximum point, this we represent as the vertex, which is 0 and 2,000. So if we were to go this way on this paper here, it might look something like this. Okay, and it's going to keep going and continue that quadratic or that parabola shape. So we know that all the way over here, run out of space, but that's all good. When it hits the ground on this side, it's going to be symmetrical, since this vertex is that axis of symmetry. So it's going to go down just like this. So if 1, 0 is 13 units away, well, this one is going to be symmetrical on this side. So we can say that this is minus 13 units over on this side. So this minus 13 we can represent as one of the zeros, which is S, and this 13 over here is our second zero, which we can call that our T. Okay, once again, this dotted line here, we can actually also identify. This is our axis of symmetry. So let's start by creating our equation that can model this situation. Once again, we are given these zeros based off our graph. So we're going to start with our general equation in factored form because that contains these zeros. So we have A y equals a, x minus s, x minus t. We know our two zeros, so we're going to substitute that as x minus. Our first one for s is going to be minus 13, so we're going to throw that into a set of brackets. And x minus, which comes from our formula or equation, t is simply just 13, so we're simply just going to put that inside just like that. We always have to simplify inside our brackets these two negatives. We can create a positive. So far we can simplify our equation to look just like that. So the only variable here that we can see is missing is this a. So what we're going to do, just like we did in the past, we're going to sub in our point of our vertex of 0 and 2000 to solve for a. And just to recall, here is our x and here is our y. So instead of y, we're going to write 2000 is equal to a. Instead of x, we're going to replace that with 0 plus 13, 0 minus 13. And we're going to continue to simplify one line at a time. This is simply just 13. This is negative 13. When we take 13 times negative 13, you're going to get minus 169. To get rid of this minus 169, we're going to divide this side by that value. What we do to one side, we do to the other. This and this is going to cancel. So we're going to be left with that a value all on its own, which is equal to minus 2000 over 169. So this, unfortunately, cannot simplify any further. So there's no common denominator. You can experiment or do trial and error by doing 2, 3, 4, etc. But unfortunately, in this case, we cannot divide by a common number here. So we can write our therefore statement as y is equal to minus 2000 over 169 multiplied by x plus 13. And over here we can see x minus 13. So in this next part, we're going to determine the distance the parachutist is off the ground at 10 seconds. Okay, so what that means, that is where the x value is equal to 10. So you can use your graph here to approximate, but what we're going to do is simply just put this x value into our equation and solve for that y value. So just to recap our equation, I know I wrote it earlier, but I'm going to rewrite it here. Stay organized. We got minus 2000 over 169, and we have x plus 13, x minus 13. We're going to take y is equal to minus 2000 over 169. We're going to do 10 plus 13. And now we have 10 minus 13. And then from here, just continue to take this one step at a time. So we have y is equal to minus 2000 over 169. This here simplifies to 23, and this simplifies to negative 3. So now using your calculator, if you can put this directly in, just put this into a set of brackets so there's no computation errors. So we're going to minus 2000 divided by 169 multiplied by 23 multiplied by negative 3. And that's going to give you a value of approximately, so we're going to put this little dot here, 816.6. Okay, so that means we can use a therefore statement, this being an application question. The units for our height are in meters, so we're going to include that. So what we can say is that the parachutist will be approximately 816.6 meters above the ground. If we look back at our graph here at this 10, so we can see that my graph here, again, you can see by my my shaky hand that this is a little bit higher. So this graph here, there is going to be some human error involved, but we can see here that it is relatively close to our answer. If we got an answer perhaps, let's say, of 2,500 over here, well, we know that we are perhaps definitely off for that. So you can use your graph as a check after you do find that answer algebraically. So that concludes our lesson for today. Thank you all for watching.